Okay, first of all, you can confirm from here that everything is all right. So display this mesh, and I will change the colors for the interior to the black. This looks nicer than this green color. Okay, next thing I will click on the check. This is very important. And then the port quality, the minimum orthogonal quality is 0.3, and that is good enough. So the any value which is less than the 0.01 is a problematic, and any value which is like a 0.3, 0.4, they are the very optimum values. And close from here, and choose that the default solver is a pressure base, which is we need in this workshop. And next thing is the boundary condition. The boundary condition is the same as we did for the NACA 0012. And this boundary condition right now, based on Reynolds number, is the 3 million. And from here, the velocity would be equal to the 43.22. 43.22. So I would be putting the same boundary condition here in the inlet boundary. And the direction will be at the 4 degrees angle of attack. So for the 4 degrees, I have the Excel sheet also. As you can see that the inlet boundary condition is 43.822 meter per second, and angle of attack is 4 degrees. This is same case as we did for NACA 0012. Only thing is that the airfoil is changed. And from here, I'm going to copy the cos component first. And I will choose the magnitude and the direction. In the x component, we are going to put the cos of the 4 degrees. And in the y component, we are going to put the sine component of the 4 degrees. And click on apply and close. And just leave everything as the default condition. Then from monitors, I'm going to click on residues and just change the value to the very lower value, so that we can the solution should only stop at when we reach the required level of the number of iterations. So let's say -20. You can copy this same criteria for the other fields also, and OK. And now we'll initialize solution with the hybrid initialization. And after that, the next thing is that you should be making the autosave of file after every maybe 100 iterations. Retain the last 5 files. And before you go for solution, again save the project. And put number of iterations to the 500 and then click on the calculate. So far we have 399 iterations, and here I'm going to stop solution because you can see the residues are now in the straight line. And first thing, we can show some results like the contour plots. You can change this to the banded, and number of levels may be 30. And then I will be displaying the velocity. And then maybe the vector plots, because you learn about these things in the NACA 0012 workshop. So you know these things very well. You can play with these options and put the scale as maybe 0.05 initially. Then one more 0. Or maybe 0.01. So this is at the 4 degree angle of attack. So that's why the flow is coming from from this point. And there may be some feeling of the separation, but it's not a separation, but this is some sort of the low momentum fluid here on the tailing edge. And next thing is, which is important here, is the forces. And before that, we should be setting the reference value. So from inlet, and the area is a 1 because the coordinate is 1, and the depth we are going to assume is also 1. Therefore, area would be equal to 1 meter square, and the length is 1, which is the chord length. And for this angle of attack, we can copy the sine and cosine from the inlet boundary condition. So copy, and for drag coefficient, we are going to put them same as it is. But for the lift coefficient, we are going to reverse the sine and cosine and choose this airfoil. So we have this value, which is 0.0136. So let me put the same value, because of this time the mesh file in this video is refined as compared to the file you will see or you will receive in the files with this course. And for the lift coefficient, this vector will be reversed and minus sign will be put in the x direction, and the cosine component will be in the y direction. Again, click on the print. So this time the lift coefficient is 0.831, which is almost similar as you can see in this PowerPoint slide. 0.834, this is a 0.8319. So this may be a 0.832. And this can be the 0.1361, 0.01361. Alright, so we are done with this fluent part, and in the next part, you are going to analyze the same results in CFD post.